Hello everyone, and welcome to our video on logarithmic differentiation. So logarithmic differentiation is a technique where we apply logarithms to equations so that we can rewrite them in a simpler way that allows us to then use our regular differentiation rules to take derivatives. So there's several reasons why we might try to use logarithmic differentiation to take a derivative. So derivatives that involve many products, quotients, and powers can often be difficult, if not impossible, to take using our previous techniques. So let's consider something like the function f of x equals x to the 2x. So the problem here is that this is not a function that we know how to deal with. We have two types of functions that look a little bit like this. We have a power function whose variable is in the base and has a constant in the exponent. And then we have an exponential function whose base is a constant and whose variable is an exponent. But in this case, both the base and the exponent contain variables. So since both the base and the exponent contain variables, then we're not going to be able to use any of our previous rules to evaluate this derivative. So first, I'm going to summarize the method for logarithmic differentiation. Then we'll break down a couple different types of situations that arise where it's appropriate to use this method. So first, take the natural logarithm of both sides of an equation, then use your rules of logarithms to simplify. Then differentiate both sides of your new equation with respect to x, and solve the resulting equation for dy dx. So as a reminder, your rules of logarithms are as follows. The product rule is log base a of x times y equals log base a of x plus log base a of y. The quotient rule, log base a of x over y equals log base a of x minus log base a of y. And the power rule, log base a of x to the r power equals r times log base a of x. So I've written these in terms of general logarithms. And just, as a reminder, just a refresher, these rules come straight from the exponent rules. These are inverse functions, so they switch inputs and outputs, and likewise, their rules switch inputs and outputs as well. So again, reminder, for example, for the exponential rule, a to the x times a to the y, you have multiplication between the functions and addition inside of the functions. You swap that around, that becomes your logarithmic rule. Multiplication inside of the function becomes addition outside of the function. Same thing for the quotient rule and the power rule. So hopefully that helps them be easier to remember. And in this case, for logarithmic differentiation, we're always going to use the natural log. So for example, we could rewrite this as ln of x times y equals ln of x plus ln of y. Same thing, we're just sticking with base e for the purpose of making our derivatives simpler. Okay, so let's take a look at our first case here. Expressions with a variable in both the base and exponent. So in this case, logarithmic differentiation is necessary. It's not just an optional approach. It's something you will need to do to rewrite this into a form where your other differentiation tools will work. So let's go back to that example we mentioned before. Y equals x to the 2x. So step one is take the natural log of both sides of the equation. So we get the natural log of y equals the natural log of x to the 2x power. And now what? Now we rewrite it using our log rules. This is x to a power, and so the relevant rule here is x to a power. I can move the power in front as a product. So I'm going to rewrite my entire equation, and make sure you are in the habit of rewriting your entire equation every step. A lot of common mistakes come from not doing that. Okay, so now we've rewritten our logarithmic expression here using our logarithmic rules. So now step two is to differentiate both sides of our new equation. So we take the derivative of ln of y on the left side, and the derivative with respect to x of 2x times ln of x on the right side. And what does that give us? Well, the derivative of the natural log is 1 over the input, 1 over y, but we're taking the derivative with respect to x here. So we've got to apply the chain rule, and so we've got to multiply by dy dx. And now for the right-hand side, this is a product of two functions, so we have to apply the product rule. 2x prime times ln of x plus 2x times ln of x prime. Now we'll clean this expression up a little bit. 1 over y dy dx equals, the derivative of 2x is 2, so we get 2 times ln of x plus 2x times the derivative of ln of x is 1 over x. Now, step 3 is to solve your equation for dy dx. So I'm going to do that by multiplying y across to the other side of the equation. So this is going to give me dy dx equals y times 2 ln of x plus, and I'm also going to simplify this. 2x times 1 over x is just 2. Just write it like that. Now, part of solving this for dy dx, though, is rewriting it as a function of just x. So remember, we started with the fact that y was equal to x to the 2x. So we can replace y in this expression as x to the 2x. And now our derivative is written entirely in terms of x, and this is our final answer. Okay, so let's take a look at some more examples of this situation where we have a variable in both the base and the exponent. Okay, find dy dx given that y equals x times x to the sine of x power. So again, we've got a variable in the base, a variable in the exponent, and we want to find dy dx. Okay, well, step 1, same step 1, take the natural log of both sides of your equation. And then rewrite it using your logarithmic rules. Again, we can take our power inside of our logarithm and move it in front, so it becomes sine of x times ln of x. And now we've rewritten it using our rules. So now step 2 is we take the derivative with respect to x of both sides. Now the derivative of the natural log of y, again, is 1 over y times dy dx. And the derivative of sine of x times ln of x is again going to require the product rule, just like that previous problem. So this gives us 1 over y dy dx equals, now the derivative of sine is cosine, times ln of x plus sine of x times 1 over x. Okay, now step 3. So we've taken all of our derivatives. Now we want to solve for dy dx. I'm going to multiply the y across. I get dy dx equals y times cosine of x times ln of x plus, and I'm going to write this as sine of x over x, just to make it a little cleaner. And the last step is to take our expression for y and plug it back in. So now we have x to the sine of x power times cosine of x times ln of x plus sine of x over x. Okay, so let's do one more example in this type of category. So we've got find dy dx given that y equals the square root of x all to the x power. Now this example is interesting because it can actually be a little more challenging to do if you're not careful in how you approach solving it. And what I mean by that is if we first rewrite this function using exponent rules, then it becomes a little bit easier for us actually. So first I'm going to rewrite this square root as x to the 1/2 power. So we've written this as x to the 1/2 to the x power. And then we remember if we have a base to an exponent all raised to another exponent, we can take the product of those exponents, and x times 1/2 is just x over 2. So now this is going to give me something quite a bit nicer to work with. So step 1, I take the natural log of my equation, and remember we're using it in this form, y equals x to the x over 2. So ln of y equals ln of x to the x over 2. Now I'm going to use my logarithm rules to rewrite this. Gives me ln of y equals, I take my x over 2, move it in front. It's x over 2 times ln of x. Now step 2, I'm going to differentiate both sides with respect to x. Now, one thing I think you'll probably notice by now, this case where you have starting out a variable in both the base and exponent typically is going to result in needing to do a product rule after you've rewritten it. That's going to be pretty common. So the derivative of ln of y, again, is 1 over y dy dx. And then on the right-hand side of this equation, we get the product rule, x over 2 prime times ln of x plus x over 2 times ln of x prime. All right, let's finish up these derivatives here. Derivative of x over 2 is just 1/2, so 1/2 times ln of x. That's ln of x over 2 plus x over 2 times the derivative of ln of x, which is 1 over x. So of course those x's are going to cancel. And so now we're on to step 3, solve for dy dx. One thing I want to mention, I'm not sure if I already said this, but you have to make sure you always put the parentheses on the right expression when you multiply y across. That multiplication has to apply to the whole thing, and that's a really common mistake where a student will just multiply this y by the first term only, not by the whole thing. So just keep an eye out for that. And finally, we will replace our y with our original expression, the square root of x to the x power times ln of x over 2 plus 1/2. Okay, so this was the first big category of problems to deal with logarithmic differentiation. So now let's look at the next category. So second case, expressions with many products, quotients, and powers that would be very challenging to differentiate normally. So these problems may not require logarithmic differentiation, but are still simplified a lot by using this approach. That's the key here. So in these cases, you could often, not always, but often use other previous approaches that we've learned, but they might take twice as long to do. So let's take a look at this one. We've got df dx, find df dx given f of x equals e to the negative x times sine squared of x over x cubed plus x squared plus 1. So the problem here is that we've got a product in our numerator. We've got exponents in both of the expressions in the numerator. We've got exponents in our parts of our denominator, but we've also got a denominator. So we just have a lot of terms here. And we could use the quotient rule. And then inside of our numerator, we've got a product. So we'd have a product rule inside of our quotient rule. And of course, that becomes pretty cumbersome to compute. So we're going to instead try using log differentiation to evaluate this problem. So our approach is still the same, though. That's the key. The technique is still the same. It's just these problems are a little more complicated because there's more rewriting we have to do with our expressions. So I'm going to write this as, we're going to take the natural log of both sides. ln of f equals ln of e to the negative x times sine squared of x over x cubed plus x squared plus 1. So our big operation, the sort of outer operation, is the quotient here. It's got the whole numerator, and it's got the whole denominator. So that's the first thing we're going to have to rewrite using the quotient rule. So remember, scroll back up to the top. When you have a quotient inside of a logarithm, you can rewrite that as subtraction of the logs of the numerator and denominator separately. Okay, so this is ln of e to the negative x times sine squared of x minus ln of x cubed plus x squared plus 1 Now I have a product between e to the negative x and sine squared of x. So that product gives me ln of e to the negative x plus ln of sine squared of x minus ln of x cubed plus x squared plus 1. Now, you do need to remember here that the definition of inverse functions says that when you compose them, you get back your input. So in the case of the natural log and the exponential function, anytime you have an expression like ln of e to a power, you're always going to get that power back, u. So in this case, the power is negative x. So we can rewrite this even simpler, and it's going to make things a lot easier for us. Negative x plus, now here, this is sine of x squared, so I can use my power rule for logarithms to put that 2 in front. And there's nothing I can do here. So a lot of times a student may try to do something with these powers, kind of a common misunderstanding. But remember that when we look at this power rule for logarithms, whatever you have inside the logarithm, the whole expression has to be raised to that power. In the case of the problem here, only these terms are separately being raised to powers. It's not the whole expression being raised to 1 power. So we can't use a power rule there. Okay, so now we've done enough to make our derivatives a lot easier. So now we can move on to step 2. And so the derivative of ln of f is 1 over f times df dx. The derivative of x is negative 1 plus 2 times. Now we've got a chain rule here, and I am going to skip the sub-steps for that. But we're going to have 1 over u, where u is the inside function. So that's 1 over sine of x times the derivative of u, the derivative of sine, which is cosine of x, minus, and we have a similar situation here. We've got 1 over u, that's x cubed plus x squared plus 1, times the derivative of that, which is going to be 3x squared plus 2x. Now I'm just going to clean this expression up a little more before I go to solve for df dx. So this is -1 plus 2. And cosine of x divided by sine of x can be written as cotangent of x minus, and in parentheses, 3x squared plus 2x. Now, another common mistake, make sure you put this parentheses up top here, because this negative would need to distribute to both terms up there. And now we can solve for df dx. So I multiply the f across, I get f times -1 plus 2 cotangent of x minus 3x squared plus 2x over x cubed plus x squared plus 1. And now we can substitute f back into our function. Trying to get this in just the right spot where I can see everything. There we go. Okay, e to the -x times sine squared of x over x cubed plus x squared plus 1 times parentheses -1 plus 2 cotangent of x minus 3x squared plus 2x over x cubed plus x squared plus 1. So these problems aren't suddenly easy just because we're using logarithmic differentiation. They're still pretty cumbersome problems, but in my experience, it tends to be a little easier, a little less prone to error to do this kind of problem with logarithmic differentiation, as opposed to trying to do this with a quotient rule and a product rule inside of that quotient. I find there's usually more opportunities to make mistakes with that approach. Okay, so let's tackle one more like this. df dx given f of x equals x cubed times cosine of x times tangent inverse of x all over x cubed plus 2. So step 1, same first step. We take the natural log of both sides of the equation. So in this case, we've got this big product here, right? We've got this whole expression here and x cubed are both being multiplied together. So here we'll use our product rule for logarithms. And we'll rewrite this as ln of f equals ln of x cubed plus ln of cosine of x times tangent inverse of x over x cubed plus 2. So another thing I want to mention, if I didn't mention it before, it is very easy to make mistakes on these kinds of problems if you don't do your log rules one step at a time. And that's it's very tempting, understandably. You want to get problems done a little bit faster, but it does make you more prone to making errors when you do that. So I recommend just applying to each portion of your function, apply one rule at a time, and make things a little easier. Now, with that being said, here I've got two different natural log expressions now. So I'll apply my power rule to this one, 3 times ln of x, plus, and now here I'm just going to do the quotient rule, the whole thing up here and the whole thing down here, and make this ln of cosine of x times tangent inverse of x minus ln of x cubed plus 2. Okay, and now here I've got another product, so I can apply one more rewrite with my logarithmic expressions. That's going to give me ln of cosine of x plus ln of tangent inverse of x minus ln of x cubed plus 2. So now we can move on to step 2. Finally, we can take our derivatives. We take the derivative of both sides of the equation. And if you'll forgive me, I'm going to skip rewriting that right side of the equation just to save an extra minute here. Okay, so next step. The derivative of ln of f is 1 over f df dx. Now let's take each of these derivatives. 3 times 1 over x plus. Now we need the derivative of the natural log of cosine of x. That's going to be 1 over cosine of x times, remember we got a chain rule here, the derivative of the inside, which is negative sine of x, plus the natural log of tangent inverse of x. That's going to be 1 over tangent inverse of x times the derivative of tangent inverse, which is 1 over 1 plus x squared, minus the natural log of x cubed plus 2's derivative. So that's 1 over x cubed plus 2 times the derivative of x cubed plus 2. That's 3x squared. And so now we got to do a little bit of cleanup. So df dx equals, well, and I'm gonna do my cleanup at the same time that I solved for df dx. So I multiply my f across, 3 over x here. I get a negative sine over cosine, that's tangent, plus 1 over tangent inverse of x times 1 plus x squared. Just multiplied those two fractions together. Minus 3x squared over x cubed plus 2. And finally, when I pop my f back into place here, which I'm gonna have to zoom out a little bit for so I can see it. X cubed times cosine of x times tangent inverse of x for x cubed plus 2. Let me check that that was correct. Okay. And then what do we got left? 3 over x minus tangent of x plus 1 over tangent inverse of x times 1 plus x squared minus 3x squared over x cubed plus 2. Okay, so before I move on, let's just kind of summarize here what this situation is. We have two different main reasons that we would use logarithmic differentiation. The first case being you've got an expression with a variable that's both in the base and the exponent. So then we have to use logarithmic differentiation to rewrite this in a way where we can apply our other derivative rules. There's no way around it. But the second case where we often want to use it is just expressions that have a lot of products, quotients, and powers involved. It's going to let us rewrite them as sums and differences of much simpler derivatives. So that's often a case where we will use them. But that's not the only cases. Those are just sort of the big picture ones where you see that you definitely should think logarithmic differentiation. Sometimes we just decide to try it out as a clever workaround to other tricky issues, and that brings us back to a topic from much earlier in the class, which was the power rule. So when we proved the power rule the first time, we only showed that it was true for integers. So we're talking about the derivative with respect to x of x to the n equals n times x to the n minus 1. So when we originally proved this, we said, hey, look, it's true for all real number exponents, but we're just going to look at the integer case because we don't have the tools to prove it right now in the course for anything other than integers. So now we have a tool that's going to allow us to prove this for all real numbers. So we're going to go ahead and do that. So we're going to first start by writing y equals x to the nth power. because to use logarithmic differentiation, we have to have an equation in this form so that we can then, step 1, take the natural log of both sides. And then I can use my logarithmic rules to rewrite this as ln of y equals n times ln of x. And so now if I take the derivative of both sides, all right, so that's our step 2. What do we get? We get 1 over y times dy dx equals n times 1 over x. Multiply the y across, we get dy dx equals y times n times 1 over x. But remember, y is x to the nth power. And finally, we'll write that n in front, and if I have x to the nth power over x, I just subtract the exponents, n minus 1. This is n times x to the n minus 1. So the point being, although typically we're only going to think about using logarithmic differentiation for the previous 2 cases, that doesn't mean that it's the only place it could ever be useful. You might find some problems where using those kinds of log rule manipulations are still useful, even if it's not one of the first 2 cases that we looked at. Okay, well, that's it for this one. Thank you for watching.